So in this video, I will show you how to implement a current controller for a boost converter. So it basically works that we have a DC voltage on the input, and then we have a DC voltage on the output. So you can see that it's changing, and that is because we have a voltage controller first. And this voltage controller calculates the difference in current, and then uses a PI controller to get the reference current that we want. And then the current controller controls the current such that the current is equal to the reference current. So that is basically how it works. Now, in order to understand how the boost converter works, how to implement the current controller, you first have to understand the boost converter. So I'll just shortly explain that. So now, if we look at how we can control the current, the only way to control it is by controlling the voltage over the inductor. Because the voltage over the inductor is equal to the inductance multiplied with the change of current over the change of time. And if you think about it, we can make the desired change of current that we want. So the change of current could be the reference current minus the actual current. So therefore, we can calculate the voltage that we want such that we get the current that we want, if that makes sense. Now, the voltage can also be defined in a way. So the voltage is actually equal to the input voltage, which is VI, and then minus this voltage. This voltage we call VM, so minus VM. Now we know the input voltage, that can be measured, but we don't know VM, or we could know. So we can actually control VM by controlling this switch here. Because when the switch here, the gate signal, which we call S, when this is equal to 0, this means that no current is flowing through the switch. So all of the current has to flow through the diode instead. This means that the voltage, VM, must be equal to this voltage, which is equal to VO. So when the gate signal is 0, we know that VM is equal to VO. And when the gate signal is 1, so S equals 1, so now because this MOSFET is closed, we know that VM must be equal to 0, because this voltage is equal to this voltage, because it's just a wire between them now. So this is 0. And now you can actually solve for VM. So VM, this is equal to 1 minus the gate signal multiplied by VO. So that is how you define VM. So you can basically control S, the gate signal, such that you get the VM that you want. However, this is not very useful because S can either be 0 or 1, which is not ideal for a controller. It should be linear for a controller. So what we usually do is that we change this to an average model. So we replace this S with a duty cycle, because duty cycle is defined also between 0 and 1. So now if we insert VM into this equation, I will just continue up here. So VL is equal to VI, which is the input voltage, and then minus 1 minus the duty cycle multiplied by the output voltage. And now we can actually solve for the duty cycle. So the duty cycle becomes 1 minus VI over the output voltage. And then we also need to remember VL. Now, what is important to remember is that we want to drive the change of current, which is over here, to 0, because then the current is equal to the reference current. This means that we actually want this VL to be 0. In steady state, it is 0 on average. So that is why I often see that the duty cycle is equal to this. However, this model is not ideal. We, for example, don't have the resistance in the inductor, and we don't have the resistance in the diode, etc. So we actually say this is 0 because it is on average. This is an average model, but instead we add a PI controller in order to correct for the errors in the model. And the PI controller is actually based on this equation here, because if you look at that equation, you can see that if the current is too low, which means that IL is lower than IREF, then the change of current must be larger than 0 to correct for this error, right? And this requires a positive VL, which is also larger than 0. So if you insert for a positive VL, as you see here, you will get an increase in the duty cycle. So an increase in the desired change of current increases the duty cycle. So that is why we have a positive sign in front of the PI controller. So that is basically how the current controller works, and I can show you how you implement it into Simulink. So you can see that we have the feed forward here. So here we have the +1, and here we have V in over V out. And then this is the duty cycle, and then this is the output of the PI controller. So this is the change of current that we have, input that into the PI controller and get the output. The desired change, this is actually the desired change of duty cycle that we want. So you can see that the duty cycle in all becomes equal to 1 minus VI or VO, and then plus the PI controller. So that is basically how you can implement a current controller. So you also need a PWM. I can just show you how it works. You have a duty cycle, and then you have a sawtooth carrier, and you just compare those.